this new IAP colloquium. It is my great pleasure today to welcome Paul Indelicato, Directeur de Recherche of CNRS at Kastler Brossel Laboratory. He's a world-renowned expert in metrology and test of fundamental interactions. He has been interested in all of them, actually, electromagnetic interaction through quantum electrodynamics or weak interaction, notably through parity violation, strong interaction through antiproton nucleon or pion nucleon interactions, and since 2012, even gravitational interaction, in fact, which is precisely today's topic. Not only had he looked at them from the experimental point of view, but he also investigated theoretical aspects related in particular to the relativistic n-body problem or radiative corrections. Paul Indelicato has been awarded several prizes and is a fellow of the American Physical Society. And let me finally mention that he has been holding several positions in research administration. Currently, for instance, belongs to the College of the HCERS. Okay, as I just said, his talk will have to do with gravitation, since he will introduce us to GBAR, a highly challenging experiment to test the equivalence principle for antimatter. So the floor is yours.
Thank you very much for this kind introduction. So yes, today I'm going to talk about an experiment which is a bit different from what I've been doing otherwise, but still based on accelerator physics. Becomes wrong. Of course, when I tried, it worked, and now it doesn't want to work anymore. I guess I have to click there somehow. Yeah, okay. So the GBAR experiment is one of the experiments which is trying to test the effect of gravitation on antimatter. And those are the different institutions which are concerned by this project, which is a bit a worldwide project. And so it got approved by CERN in 2012, and we have been working on it since then. So here you have the list of the people involved in GBAR for the collaboration, and then the different teams of Laboratoire Kastler Brossel which are implicated in this, from both experimental and theoretical side. So at first I will tell you why there is an issue. Wow, I've forgotten I had done that. So the question is, you have an apple, the Earth, you still have the Earth, but then you have an anti-apple. It's easier to make an anti-apple than anti-Earth, of course. And so the question is the attraction the same? That's a fundamental aspect. And there are a lot of things that are being done about the gravitation and the test of special and general relativity, the test of the Lorentz invariance, the mass energy equivalence, gravitational redshift, of course, like the Faroese satellite we should have flown a long time ago, but it's still in a box somewhere waiting for a space in the space station. The equivalence principle, and for example, a microscope, I guess you have heard about that one, which is comparing the gravitational effect on different material in space, in a satellite. Gravitational waves, I guess I don't have to talk to you about that. And there have been also measurements of the ratio, for example, between the antiproton and the proton masses and the magnetic moment, the Bayes experiment. And so the question is, what about the equivalence principle between matter and antimatter? So there have been a number of papers which, for example, anti-gravity, a crazy idea by Mr. Scherk a long time ago. And then studies about, is it true that if you say the general relativity is true, and there is nothing special about antimatter, and so there should be no effect? And so, of course, one of the big objections to specific effects is a violation of energy conservation. If you assume that you have a bit of matter, a bit of antimatter, and there, for example, repulsion between them, they will fly away forever and then create energy, right? So it's a real issue. And it's, of course, a violation of the equivalence principle. And an experiment on the K mesons, which seems to show that there is no effect. But the thing is that all these arguments are, of course, important, but they cannot rule out every kind of difference between matter and antimatter. So the gravitational effects in normal life, although we are, of course, standing just because of them, are very weak. If you have an electric field of 10 to the 7, 10 minus 7 volt per meter, sorry, that's made a small v, it's a large V, of course, capital V, then that is enough to counteract the gravitation. And also, if you have a magnetic field of 10 minus stellar acting on a charged particle, also that will have a big effect compared to gravitation. And so on the low energy antiproton ring, which was the ancestor of the current machine at CERN, they try to measure the effect of gravitation on antiprotons, and what they observe is the stochastic motion of the antiproton due to the different charges that were deposited in the metallic parts, and they could never really get to an answer. And so one has to use a neutral particle. So, of course, one of the ideas is to use antihydrogen, which has been synthesized for now many decades. And there is also an idea at the Paul Scherrer Institute, which is to use muonium. But the problem of muonium is that it's short-lived, so it's not so easy. Normally, the antihydrogen lives as long as the hydrogen, so forever, basically. And of course, you could imagine to use heavier particles, but the only ones that you can produce really in large amounts are the antiprotons. Actually, at CERN, they also produced anti-deuteron and anti-tristons, that is the tritium antiparticle, and also anti-helium-3, apparently, on the higher energy machine, but they cannot send them back to the low energy part. But in the idea, they have anti-deuterium. So, but only a few of them. So antiprotons still to be the... And then, of course, to do antimatter and antihydrogen, you need antiproton, but you need also anti-electrons. Otherwise, you cannot make a neutral particle. So you need also an intense source of positrons. And most of the experiments until recently, until GBAR, they used radioactive samples, sodium sources, which emit beta radiation. It's getting difficult now because of the problem with Russia, of course, because most of those intense sources were coming from Russia, apparently. Okay. So there have been several experiments besides GBAR, so I'm going to advertise them also. Not, we'll see what happens when you try to do this kind of experiments. So, the first one to publish the result was BASE. So BASE is really to test the CPT theorem comparing protons and antiprotons. But because they take data for a long time, then there is a variation of the gravitational field due to the rotation of the Earth around the sun. And so they can measure at different times and compare if there is any influence eventually of gravitation. So it's rather indirect, but that they did. And so so the way it works is that they have this very complicated system of traps where they can have, for example, an H minus and an antiprotons to have the particle with the same charge, avoid some systematic effects. And they then compare their masses. And then they can have the ratio of antihydrogen to protons. So of course, there is a small difference because of the mass of the electrons. Then from that, they can deduce the ratio of proton-antiproton mass, which is quite close to 1. And also they can get an estimate of the difference between the gravitational constant for antiprotons and for protons. So that was in 2022. But then, of course, you have a big magnetic field, and it's a complicated experiment, so it would be nice to check by more direct ways. Then the second experiment is alpha G. So there was an experiment called alpha, which was one of the pioneers in making antihydrogen. And so they basically made the same experiment, except they made it straight in place of being horizontal. And so it was vertical. So they are also trapping antiprotons and anti-electrons and positrons in fields where they can meet. They can also cool by trapping electrons and having the edges which are at the liquid helium temperature. They can also cool the antiprotons. And then they make antihydrogens that they trap in a magnetic trap. And so they published last year a paper where they did experiment. So what they do is that they have detectors above and below, and they compare the intensities they observe in both cases. And then they can add a small magnetic field and measure the ratio of what they observe up and down. And from that, they deduce that the gravitational constant for antimatter has the same sign as one for matter, which is not necessarily what we would have liked to see. It would have been more fun if it had been the other way around. And then they get some statistical and systematic errors. And they claim in the paper that the probability that GBAR is 0 with this measurement is very small, and that it is negative is really very, very, very small. So after that, I know people who have claimed, but they didn't publish a paper, but that because of all this trapping and everything, it's again quite indirect, and you cannot really be so sure. But anyway, see that. After that, you have another experiment which is called AeGis, which has done antihydrogen by trapping, making a positronium and having antiproton capturing the positron from the positronium. And then they use a relatively fast beam of antihydrogen, so they made that. And then what they want to do are Moire fringes. So those are fringes made with a grid which have different step size. And that's what makes some clothes shiny and changing colors when you change orientation, because you have all those wires which are shiny with different step size, and then that makes Moire fringes. And so the idea would be to look, because you have an horizontal beam, that it goes slightly down by looking at those fringes here on the detector. For the moment, they didn't try that. So, I mean, they have not yet done that part. So it's less advanced than the two previous experiments I showed you. And so you have, as usual for the experiment, it's a complicated thing where you have to recover your positrons from some radioactive sample, get them into a trap where you have your antiprotons, make this antihydrogen, and then detect the eventual change in orientation due to gravitation. They have been able to cool the positronium to prepare for that. And so this is a bit the status presently. So now, coming to GBAR. So the idea is due to Jürgen Walz and Theodor Hänsch. And so the thing is that if you cool antihydrogen with lasers, you have a limit which is due to the recoil, and when you absorb a photon, you recoil. And so even if you have several lasers in several directions, everything, there is a limit. That has been known from the work of Claude Tuantalgi and et al. For a long time now. You have this limit, which is a minimum temperature you can get by laser cooling. Now, if you use a charged particle and you cool it with a different system, which I will show you in a short time, then you can cool down to microkelvins. Typically, you could cool this ion, which would be antihydrogen plus one positron, which is like H minus. You could cool it down to a few microkelvin. And then if you drop it, so you have to break it because it's charged, but you can do that with a laser and without communicating vertical speed. And if it falls down, then it's a time long enough with this temperature that with a small 8, you can measure precisely the dropping time. So that was the proposal of Hänsch long time ago, now 20 years. Sorry. And so you have your anti-H-bar plus, H minus, anti-H minus or H-bar plus here, trapped. You cool them. With a laser, you break, you remove the extra positron, and you measure the falling time. And so for 20 centimeters, it's 200 milliseconds, so that's a very easy time to measure. And so the expected precision, if you can do that with enough H-bar plus, would be going from 2%, which is already slightly better than what I showed you before, for 1,000 of them. And then up to 10 to the 5 and 10 to the minus 3. And I will show you at the end that if you use the quantum effects, you could even, with a smaller number, you could go even better. And so you have to have antihydrogen to do that, positrons in some way, make them interact and the antihydrogen capture. Then you send that in a trap where you cool by mixing them with beryllium plus, which is cooled by laser. That's the well-known technique. Then you do a photodetachment just as a threshold, which you have to know, and that's not so easy because actually we discovered that it was not so well known, even though it's a simple system. And then you measure your fall. So now this is nice, simple, but then you have to do it in real life, and that's another story. So first you need antiprotons. So since LIR was shut down in 97, where I think I was in the group which was the last to use it, low energy antiproton ring, because I wanted to use it to make lead for the LHC, and I thought that having also antiprotons was an issue. Okay, so in 2018, they started a new small ring, which is called ELENA. So you need to make an intense beam of protons, send it to a target. Then in the collision, if you respect the energy condition from special relativity, you can get protons and antiprotons pairs on top of the incoming protons. And then they store that in a ring where they cool them because they are very, very energetic and also very large distribution of speed. And then they send a second ring, which they can decelerate and cool them more, using both stochastic cooling and electron beam cooling. And then they are still at 100 keV kinetic energy, so you have to decelerate them again to get in the range of a few kilo electron volts where you can make those reactions to make antihydrogen. And so in the GBAR project, we will send that on a positronium target. And then after that, normally in 2 steps in the same target, at some point you should get H-bar plus ions and then use them for the experiment. So you have to capture them in a trap, cool them, and detect them. To make the positrons, we need much more positrons than one radioactive sample can make. So the idea was to install a linear accelerator, a small one, which go like 10 MeV, make fast electrons, send them into a target. You get positrons in the same way that you get antiprotons with the proton-synchrotron for the CERN part, and then cool them, trap them, and send them to make the positronium in the target here. So since you have the 2 ends which are covered. So just to give you an idea, so you have ELENA, this is a relatively small ring. So GBAR experiment has been implemented here. You have here what was alpha before, still there, which is the alpha G, but horizontal. And here is this bunker with a lot of concrete is where we have to put the small LINAC because the radiation is huge. And then, so you have the LINAC hidden somewhere here. You have a line where you make your uncool your antiprotons and trap them. You have your your anti-electrons. You have your antiprotons coming from ELENA, which is here. And then you have your experiment and then, well. So we have been constructing all that. So ELENA, you see the p-bar in the AD, they have at 3.5 GeV over C. So they had deceleration, stochastic electron cooling. And then if you put here a degrading foil, then to get to a few keV, then you lose almost everything. So in order to avoid that, they added this ring, which do deceleration and cooling up to down to 100 keV. And then if you have some target and stuff like that, then you will, on a window, you will have very thin, of course. Then you can go to a few keV, but you lose only 20%, which is much, much better. And so you see that's a typical storage ring where you have a radio frequency cavity, magnet, focusing quadrupole. And somewhere here you have the electron cooler. So these you have electron beam which go along the antiprotons and with Coulomb interactions, the antiprotons get cooled. And because you throw away the electron all the time, they stay cold because you have always new. And at the end, that was invented at CERN and used a lot of time at GSI also. And that's the way it looks in real life. And of course, all of this is in ultra high vacuum, 10 to the minus 11, so that you don't use your antiprotons because they do many, many, many turns, of course. So the positrons, we have to use this LINAC, and that has been something which was tested first at Saclay with a smaller one. And then another one was constructed by a Polish group who is contributing to the experiment. And we are using that one, which was installed at CERN some years ago. And so the thing is that you have a target which is a tungsten target, where you do the collision, which provides those positrons. And of course, you have also electrons, so you have to get rid of them. Then you have some moderator to reduce the distribution of energy. And then you make them slow positrons, 3eV, which is sort of slow, but not that slow if you want to go to very low temperature. Kelvin is, 1eV is a lot of kelvins, as you know. And so this is the way it looks. So you have this part. No, I don't want to shut my computer. I don't know what happens. I don't know what I did that I wanted anyway. So you have here the LINAC, and there you have a target. And one of the issues with which we have had a lot of trouble is that the target, even though there's a lot of concrete around, the radiation is so strong that, for example, all the plastic tubes, a lot of the covering of electric wires and everything, which you use for manipulating things around, because of course you have to do that all remote control, they burn with time and they break, and so we still have problems. Even the klystron, which makes the radio frequency for the LINAC, also gets damage over time. So this is really a difficult part. But on the other hand, we get many more positrons than you would get if you were using a radioactive sample, at least the one you're allowed to have in a lab environment. And so you have here all this concrete is around this accelerator. It was built only for that. And you need all this thickness and to be sure there is no big radiation, because at the AD, you can walk around here, for example. So all this part, when the machines are running, you can still get inside. You cannot just get down there, but you can go around. So of course, you don't want to have here a huge amount of radioactivity going on. And that is a picture of the LINAC. And so you see, you have to have this with the concrete so that the high energy particles which are there are stopped, and you extract only the one you want. Otherwise, it would be still an issue. And you have, of course, every magnet that allows to bend the beam and get it out. Or with electrons, it's not so difficult, or positrons. So you can see here, so this is simulation using the CERN software GN4. You can see that the optimal target thickness, where you get the most of positrons stopped, after the place where you make them is around 1 millimeter, so that you can use a 50 micron thick tungsten moderator. So that's what we have. We have a target which is this thickness. And so now we have been producing that for quite some time. And now, so for each pulse of the LINAC, you can go up to 300 Hertz. But in practice, we use more around 200 Hertz because otherwise in this place, it gets problems pretty fast. So per each pulse of LINAC, you get this number of positrons depending on the frequency, and per second, this is what you get. So you get about 3/10⁵ per second for the experiment. And here you can see the drawing of the line where you send them afterwards to in each, so they get here in, and then you have places with gases in which you slow them down, and those are magnetic field with coils and everything, so that you can trap them, cool them, and then prepare them for being sent to the target. So you see, it's quite a complicated. This is the pictures. You see, they're kind of complicated, a lot of electronics, a lot of cabling, and all these things. So that took some time. That's the other side. So you see the positrons are coming out of the bunker here, and they go to the experiment. It was not yet connected, but they go to the target here. And you can see the complexity. This is those are the magnetic fields depending on which phase of the trapping and cooling you are, and so you have to synchronize all that, synchronize all those magnets, A, B, C, D, and so forth. And the brown part are magnets. And of course, the gases that you put in a different place. This is not, I mean, nothing you can do in a day. And but now it's working reasonably well. And then you change the, you change the, no, sorry. You have to change the different trapping potential so that you can extract the positron at some point. And pressing that too hard. And you can see now when you stack them in the trap, you can reach like 1.6 10⁹. That's what we published 2 years ago. And this is the ejection potential. So you stack here, then you increase the potential, and when you get there, they're ejected. And just a few weeks ago, there was optimization done by the people working on site, and they were able to go up to 3.5 positrons. So that has been improving steadily since a few years. But it's always tough. So then you need to make positronium. So positronium, it's relatively easy to do, actually. You take nanopore, silica with nanopores, and you get the positrons in. They capture, they capture an electron, and then an electron from the solid, but of course it's under vacuum. And then because they become neutral, then they get out and they can diffuse. And so you can get from all those pores, you can get your positrons out, actually, because of course it was thick material, it would be more difficult. And then you can really make, there is a part of the positronium which lives like 142 nanoseconds, which is a sort of long. And so then we can use them for making the antihydrogen. So again, we have ELENA, we get the antiprotons, we get our positrons, and then we have this reaction chamber, and then antihydrogen out. And there is a system which allows the antiproton which didn't react to go away. So this is a decelerator that we built. It was built by the team at ECG Lab to go from 100 kV to a few kV. So you have a drift tube, that is you get the antiprotons inside, it's conducting material, and then you change the potential of the drift tube. And because they are inside, they don't see that it changed, but then they go out, of course, with the energy of the voltage that you apply to the drift tube. And so you trick them in thinking they are still at high energy, but they are low energy, and they get out with a few kV. So that's a standard method. And so we have now a few kV particles, antiprotons that we can use. Of course, you need to do all the experiments. So we have the decelerators that I just showed. Then you have some transport, and then you have your target. And at the exit here, you have, I will show you in a second, you have something to eliminate the antiproton which did not react, and here again. And so normally, if you were doing in a normal way, you will have some antihydrogen going straight, anti-H minus going one way, antiproton going the other way. We have all three particles at the end. For the moment, we don't have the anti-H minus. So we did in 2022, we had our first antihydrogen. So you have your anti-electrons going in. Then you have this chamber where you have this target I just showed with this silica moss. And then that's where the antihydrogen is made. So you have your positroniums, which are emerging from the target. So they make a kind of cloud through which you have to guide your antiprotons. And some of them capture positrons and get out as antihydrogen. And so if you look at this, we have the positronium. So with the target, so you have a simulation that was done. You have the experiment, you see the purple line. And then if you look at that, you have we can show that there is about 18% of the positronium which are in the in spin 1, which have 142 nanoseconds. And the spin 0, the parapositronium is very short-lived, is 125 picoseconds. And so that's we cannot use, and we don't live long enough. So we can get only like 20% of the positronium we make is in the state where we can use it. That's why we need a lot of them, of course. So as you can see, you have here your positronium. Here you have an image of what happens inside the target. You see the radiation light from the decay of the positronium, which turn into 2 gamma rays. And then you have your antiprotons, and from time to time you get an antihydrogen going out. And then this is a bender, so the antiprotons get out of the way. Most of them, not all of them. And then we have a second one later on to get rid of the rest. So you see it here, you have the target. When the antiproton gets to the wall, then it annihilates with a nuclear material there, and they will get pions. And here you have MCP. So if antihydrogen flies straight, of course, because it's neutral, and so you can detect here normally only antihydrogen, and then the remaining p bars, they go away here. So this is like 1.7 meter. On top of that, I will show you at the end, we put a Lyman alpha setup so that we can eventually look at antihydrogen spectroscopy. And so here you see experimental bunches. When you don't do anything, you don't put a target, you see how much time it takes for the p-bar to reach the detector, which is on the straight axis. And that gives you the window that you want to put to detect antihydrogen because the flight time is the same. And so this is, and you see the fluctuation due to the jitter of the different part of the accelerator, and also the high voltage of the decelerator fluctuations. Even though they are very well stabilized, they're still enough that you see all these small changes. So now, of course, to know that you have done antihydrogen, you have to get you have to know what the background is. So you look at this window as it showed, and you send some beam without positrons in the target and some beam with positron in the target. And of course, the background is about the same. And it's coming from the pions, because even though you suppress the antiprotons, when they get somewhere, they make big 3 pions, which can go anywhere with their very high energy. And some of them can get to the detector. So you have to distinguish those. So that's why we compare the 2 cases. And you can see the background is about the same for both cases, because in all cases, they end up being annihilated at some point. But then when you have the one which have met the positronium, you get high energy pulses, because of course, if you annihilate one antiproton in the detector, it's much more energy than if you get a pion inside it, because it has, you get 2 GeV of energy in place of like 100 keV or 100 MeV or something. So that's how we can detect them. And we have other methods. I show only one to not to be too long, but we have other methods to ensure that what we see really antihydrogen. And so in 2022, we made our first antihydrogen, and we're able to detect it. And you can see here on the detector, which is on the axis, which has this diameter here, you can see one of those events when you have an anti-hydrogen hitting the detector. So now the next step, which we haven't done yet, and one of the issues at the CERN, we had already a 2-year stop of the CERN because they were doing the upgrade of the LHC. And at the end of next year, they will switch off again everything for 18 months for the next upgrade. So it's sort of a bit tense. And so one thing we learned like a couple of years ago is that there was a new calculation of the cross-section to make this H-bar plus from the collision of H-bar and the positronium. And we used a paper which was published in 2013 and some estimates that were done earlier. And it appears that the new cross-sections are much smaller, like 2 orders of magnitude. So part of the experiment now is to, so you make H minus with a proton beam, because the proton beam we don't CERN, we have a small proton source and we can do it by ourselves, and it's much more intense, of course, than antiprotons. And so that we can confirm the calculations for the cross-section. Because, of course, you have your clouds and you have your antihydrogen, which is flying inside the positronium cloud, and it has to do 2 capture. I mean, the antiproton has to do 2 capture, one to become antihydrogen, and then another one to become H-bar plus. And for that, we may have also to excite the best case is when the antihydrogen is in the ground state and the positronium is excited. So we also need laser to excite it. And so that was a paper which was done at the time showing the cross-section depending of the state of the positronium for one hydrogen, antihydrogen, the 1s. But then they found out that they had numerical problems when they did the calculation. And there was another paper done about the same time. And so you see 10 to the 1, 10 to the 3. So it's not quite. So that's much more difficult than we thought when we got started. Which means that we have, this is the new calculation done by another group. And they sort of agree that there is like a couple of order of magnitude less cross-section. But the best way, cross-section are difficult to calculate. It's already a relatively complicated system, so we have to, the best way is to measure that. So what happens next if we ever get those H-bar plus? Well, this, you can see the cloud. This you send laser, which is tuned through the beryllium plus transitions that you have here. And this is a light which is re-emitted by the beryllium plus ions that you are cooling. And so you can see, and if you inject particles inside that can be cooled, then you will even see some black dots because they won't emit the light. So you can send, for example, HD plus or D plus. There have been measurements done for some times. And for other applications, and we have a group at LKB who is also working on H2 plus or HD plus. And the way you cool is that you use your laser. You are trapped in a pole trap, and so it's like a level harmonic oscillator. And so you excite with the lasers, and they make spontaneous emissions. And if you do it right, at some point you can get all your things go down and down and down to n equals 0 in the trap. And then you get ultra cold beryllium plus. And when you are there, if you inject a charged particle, it will do a Coulomb exchange. Because it's the same sign, it will keep away the trapped particles. And then you get the... and so that is the idea. First, trapping this H-bar plus in a big cloud of beryllium plus to start cooling because they will be hot at the beginning. And once they are cool, you extract it and send it in a precision trap where there will be only a single beryllium plus ion and a single H-bar plus ion. And then you can cool it even more by just this 2-particle interaction down to the 10 microcoulomb. So in the collaboration, there's a group of Ferdinand Schmidt-Keller, who is the expert on this kind of ion cooling and trapping, who is also working here with us. And you can do simulation to show that you have to cool on the 3 directions, of course, and how much it takes depending on the initial energy of the H-bar plus. So that's something we have to optimize. And again, that will be tested with matter ions, and we are testing that in the lab actually in Paris. Okay, so in this case, if you have that, you have your anti-H bar, your anti-H minus that flies there, and that will end up in this target. And you have all the lasers which are already installed that should do the job. And here you have Laurent Helico, and that's LKB in Paris, and you can see here how it looks when you have the trapped ions that are emitting lights. This is a real picture, it's not a simulation. And then you see the kind of electrodes, and so these are all accurate mechanics and difficult things to do. And so you can test that by using other elements. So there is a group at Paris University who's collaborating with us and do the same thing, because there is one problem to trap beryllium plus, which is a mass of 9, and H bar plus, which is a mass of 1 in the same Paul trap. It's the extreme you can do. And so to test that it works, so that we don't have to have some intermediate mass, they have been comparing 2 different atoms, which in the case would be beryllium plus and another. So already as a first step, in Ferdinand Scalar group, they did the beryllium plus and calcium, and in Paris, in the University of Paris, they do even heavier elements, so that we have the same ratio about 9, and we show it in a second. And then, of course, you have to do the photodetachment, and for that, you need to measure better the H minus photodetachment energy. And of course, you put a laser horizontal so that it won't give vertical speed. Otherwise, it would not be useful to cool before. And so you have the free fall chamber. You have to have detector all around to detect the pions that will be emitted when you hit the ground and know that it's there. And of course, you have a speed distribution. So some of the H bar will go up and some will go down. And but at the end, it's like if you throw something away, it will always go back down if G is, of course, same sign as for matter. Now, if you want to go further, then we have a group, LKB has been expert in interaction between atoms and surfaces. And so you could make something like that, those 2 disks. You have your antihydrogen cold will bump. It has been observed with other cold atoms. And then you could do something like that, have several bumps, and then it falls down. And with that, you can improve the accuracy, just not measuring the free fall, but several oscillations. So that's for the near future. I mean, of course, we have still depend on the fact that we can make a H bar plus, but if it does, then you can think about this kind of thing. They have studied what kind of surface, probably liquid helium. So it's not easy, but that could be doable. And so those are simulations of what happens, and you can see the different times and depending on the initial speed where they hit the floor of the reaction chamber. And that is a plan. So we haven't built it yet because I mean, it's quite expensive. And if we don't have a H bar plus, then we don't want to. So we wait. And meanwhile, so we are doing a lot of developments around. So there have been several funding to do this mass ratio of 9 by cooling beryllium plus and strontium plus, which involves the MPQ lab and the LKB. You have another ANR to measure the cross-section of H minus production to check the theoretical calculation, which is head by Pauline Comini. There is another ANR to measure the energy of the H minus photoionization, LKB and a group in the laboratory for plasma physics. And then there are experiments around, and one of them would be using the same beamline and system to measure antiprotonic atoms. And so Nancy Paul, who joined my group a couple of years ago as a senior researcher, has got an ERC grant for that. And so we will do also those kind of experiments, because you can always use the antiproton which are not used by something else to do other experiments. One of the ideas we proposed some time ago, because we have also some trapping experience with ions, would be to put here a reflection mirror something like there is a system of trap which is called electron ion beam trap, which you could use as a mirror to send the antiproton back so that they could interact several times with the target so that you don't lose them. So that would be also a way to gain. You have that's the experiment I showed before. The positrons coming in. You have your HBAR plus that we use. HBAR that can be used for other experiments. And then the antiproton which are lost, which will be most of them. So if you could reflect them back, which is not easy, one could have much more antiprotons to use. So that's there have been simulations done at the ECG lab in Saclay. And so the other experiment, one is to measure the lamp shift. So we have your antihydrogen flying through. And so you can put a microwave and hyperfine state selector here. And then look at, depending on the microwave frequency, look at the emission of Lyman alpha. That's the original lamp shift experiment. And so there have been many experiments measuring 1s, 2s, or 1s, 2p transition in alpha to check the CPT theorem, verify that you get the same energy in hydrogen and antihydrogen. Here, the idea would be to check the 2p, 2s transition because it's a bit more sensitive. You don't have this order of alpha square classical energy. It's just a lamp shift. And so it's a bit more sensitive to CPT theorem than the direct 2p1s transition. And then we have this ERC project where we use some microcalorimetric detector, X-ray detectors to measure transitions, for example, in antiprotonic krypton. With a normal detector, you get the red curve, the standard ones that have been used for a long time. With those microcalorimeters, they have much better resolution. And for the same thing, you will see this kind of line. So they are much more narrow. And so you can, with a good calibration, you can get orders of accuracy, order of magnitude accuracy better. We did experiment like that with the usual germanium detector at Lear many years ago before it was closed down. So now the idea is to use those new quantum detectors because you use quantum amplification to do new experiments with muonic atom to test QED. With antiprotonic atom, sorry. If you look here, you have, for example, this is the binding energy, this is a logarithmic scale. The nuclear effects for helium-like uranium, which have about the same energy as antiprotonic xenon, the 12O to 11 in transition. So it's a circular Rydberg state. You have the self-energy, which is big in this case, which is very small in this case. So nuclear corrections are very small because it's this planetary kind of atom. And then you have a huge value for the vacuum position relative to the transition energy. And the second order QED is more important than it is in normal highly charged ions. So the idea is to test that by using the remaining antiprotons. So we have proposed this experiment to study antigravity using ultra-cold neutral antimatter. And so for the GBAR project is to use HBAR plus ions and using the AeGis, antiproton decelerator, ELENA, a trap, and ELENA. I forgot to mention, we're also developing a trap. That's our people from Korea, which will allow to trap the antiprotons in between the decelerator and the target so that we can accumulate them and use them when we want. Because a part of the issue with ELENA is that the bunches are very short. So with that, we'll allow to improve also things. And so if we we are successful to produce HBAR in a fully quantum regime, then we can get the best possible accuracy. Although we have this issue of the theoretical cross-section that went down quite a bit recently. And so that means that each part of the experiment has to be much more efficient so that we have enough. And then we can improve if it works using quantum reflections to be able to do more accurate even with a small number of particles. Thank you. So,
okay, it's time for questions. So I don't know who was the hand first, but
Very nice talk. So as you can imagine, I'm not an expert on this. I guess the requirements for the amount of vacuum you need inside your experiment, those things have been very well understood inside CERN, so it's not really an issue.
So we have a constraint which is very strong, is that in the ring, they have 10 to the minus 11 millibars. And so we have to be as good, because otherwise there is a valve that automatically closes. So we are completely disconnected. So normally we have 10 to the minus 11 everywhere, which means you have to bake up everything to put, heating ribbons around, heat, and every time you do something inside, you have to wait until the vacuum is good enough to be able to open to the ring.
Yeah, so I was obviously very impressed by how extremely complicated your experiment is.
Yeah.
Given the fact that, I thought Euclid was complicated, but you guys are another order of magnitude. Is there not an easier way to make these particles, for instance, by colliding much heavier atoms together? Is there not a chance that you would get some?
The problem is the energy you need. You need the proton synchrotron that is used at CERN to make the antiprotons. The energy is 27 GeV. So it's you could collide heavier ions, but I don't think you could get. I mean, of course, then you are handicapped by the fact that you have also neutrons in any other, and so the relative energy would be smaller actually.
You get a lot of garbage in the collision.
Not only that, but also for the identical energy, the energy per particle in the nucleus would be smaller, because you have the one who cannot which are not sensitive to the electric acceleration. So it's they do actually observe this kind of things in the when they do lead collision in LHC or in the SPS, so the higher energy particles. They do observe some of those nuclei, but then they are very, very, very fast, and you cannot slow them down enough that you could use them afterwards.
Yeah, here. What's the theoretical motivation to consider that antimatter could react differently to gravity than matter?
Well, there have been several papers. I mentioned them at the beginning.
No, but
one idea behind that, I think, is that you don't observe antimatter around you, right? And so the people thought that if there was repulsion, then antimatter would be on one end in the universe and the matter at the other end. And so that was a kind of idea. And then some people developed models that seems to lead to even opposite sign in some cases. And probably it's not true, but still the models are solid enough, at least this kind of, that you cannot just dismiss them just by saying, well, that's just not true.
And what kind of models are you talking about?
Well, that's not really my domain of expertise, but there have been several papers that I showed at the beginning where specialists, Nieto and others, they looked at that. And Joel Scherk, I think, if I remember correctly, was one of the founders of, the theory where you have 22 dimensions and the particle are all small wiggling string theory, sorry. So there are some models, including related to string theory, that may show such a thing. So,
but he would be going way beyond what we currently know, right? I mean,
I'm sorry?
If you want to couple in a very standard way, for example, matter fields to normal GR, it's impossible to get stuff that react differently.
Sure, but
if there would be a difference between the acceleration of hydrogen atom and antihydrogen, probably the main reason would be that this is due to a new field, should be a vector field,
yes,
because the interaction of scalar and tensor acts exactly the same way on particle and antiparticle. So that would be the evidence of
if you are having the opposite sign seems to be difficult, but having a slightly different because of fifth force kind of interaction that we are just saying could be. So that's why you want to measure precisely if they behave not just the sign, but the ratio of GBAR to G, to be sure that there could be one way to find some new kind of interactions, of course. If you get into the standard model, of course, there is no way, but...
Thank you for the talk. If there is a difference between gravitational interaction of matter and antimatter, then CPT is violated. Now, there is, from particle physics, there is a constraint on the violation of CPT. I don't know if the GBAR can achieve, I mean, is comparable from the precision or something.
Yeah, of course, it's a violation of CPT. And that's one of the tests that is done both at LHC and at low energy. Alpha is trying to test CPT for hydrogen and antihydrogen from the electromagnetic part. The base experiment that I showed at the beginning also tried to do that by comparing the mass of the proton and the antiproton, and there also the magnetic moment, because also they are normally to be exactly equal if CPT theorem is not violated. And then you have also a bit of a strong interaction involved. And so, of course, it depends of the, as you know, there are a lot of possible interactions, so dark matter and all these things. And they have eventually different mass range, different, there are so many models. And so you could think that one case would be okay and one case would be violated because of some strange particles like the one, depending if they are scalar particle, vector particles, and all these things. So you have to test. I mean, we are, you know, you look for your keys under the lamp, right? So we are saying things we can do, and nobody knows where to look really. And all the experiments from astrophysics, as you know much better than me, up to now, all the fifth force and whatever, they don't seem to. We don't really understand what dark matter is, not even to mention dark energy. And the more observation, I mean, when I read the papers, it's not my field again, but you see, it seems to become more and more complicated. So you just try to do a number of precision experiments and see, like the microscope one, for example, if the two, I forgot what it was, platinum and aluminum or something like that, they fall in the same way when they are in gravitational. They are in a satellite and all these things, and you try to find a place where, and you test better and better and better. Maybe at the end we find that there is no effect, but if we haven't tried, we cannot know, I guess.
Well, Paul, thank you for your talk. Very interesting. It opened my eyes. And so I want to go back to astronomy. To test the gravitational effects on antimatter. Another type of antimatter is antineutrinos compared to neutrinos.
Yes, exactly.
And so astronomers had the luck of having a star explode in the next galaxy, supernova 1987A, and the delay time between the neutrinos and the antineutrinos might be proof of a different reaction to gravity. And the data was not fantastic. So my question is, before the next one, the next supernova explodes, this time maybe in our galaxy, and we'll see it much better and we'll have better detectors, would it be interesting and is it possible to make experiments in the lab with neutrinos and antineutrinos?
Yes, I think they exist as T2K in Japan, which the laboratory, the LPNH is contributing. I'm not quite sure if they see both neutrinos and antineutrinos, but I would guess so. So they send a beam from GBAR, etc., where we do other kind of experiment to a fixed target. There have been also, there is an experiment in the US, which is also with the Fermilab, which is trying to see this kind of effect. I'm not quite sure about this neutrino, antineutrino thing, but I would guess that if you make neutrinos, you have to make as many antineutrinos, but I'm not quite sure. But also, and there is also one with the nuclear power plants in France, where they look at the neutrinos emitted by the core. So there are, and CERN, I think, also is doing one. You know, the famous one was they measured the big effect because the cable was not well connected a few years ago.
That was the one with the Italian, there was a link between through the Alps.
Yes, that's the one, yes. And at some point they thought they had found a fantastic effect, but it was a problem of propagation in the cable, which had a problem of connectors.
Thank you. So unless there is a very urgent question, I suggest to stop here and thank our speaker again. Thank you. Thank you.